Hi everyone, Samar here, and welcome back to Code DevOps. So in the last episode, we explored container images with the frozen pizza analogy, and today we're peeling back the packaging to look at the layers inside the image. So think of it like in the individual ingredients or layers of toppings in the pizza, and each one plays a role, and together they create the final product. So let's start with the basics. So what exactly are container layers? A container image isn't just one big block. It's actually made up of layers, which are read-only file systems stacked on top of each other. And each layer represents a change or an addition to the image. So for example, one layer might install dependencies, another might copy your in your application code, uh, another might set configurations. And now here's the key part. When you finally run a container, a writable or container layer is added on top of the stock, and this layer is the only place where runtime change actually happens. So everything below stays immutable and consistent. So to make this easier to picture, let's use a pizza analogy. So the base layer is like the pizza crust. The middle layer are your cheese, your toppings, all the extra components that build up your image. And we finally have the writable container layer, which is the hot pizza you actually eat, and it's where the live modification happen at runtime. So in simple terms, container layers are the building blocks of images stuck together with a small writable layer on top to allow your container to run and to adapt. Uh, all right, let's see now how container layers actually work in practice. So when you build an image from a Docker file or container file, each instruction creates a new layer. So for example, you can start with a base image like Python 3.11. So that's your base layer. Then if you copy in a requirement file, that's another layer. If you run pipe install to add dependencies, that's another layer. And finally, when you copy your source code, that's also another layer that will be stacked on top. And all of these layers are actually read-only and immutable. And once created, they don't change. But when you run the container, Docker adds a thin writable layer on top, and that's where any changes at runtime actually happen. Okay, now let's take a closer look at what really happens inside a running container. So every container starts from an image that's built from multiple read-only layers, and these layers are immutable. So once they are created, they can never change after. But when the container actually starts running, we have a new layer that's created. It's the writable layer, and we can also call it the container layer. And you can think of it as a temporary workspace that sits right on top of those read-only layers, and it's the only place in the entire container where changes can happen at runtime. So if your application writes log files, creates temporary data, or downloads small updates while it's running, all of that goes into this writable layer. And you need to know that this layer is ephemeral. So when the container stops or gets destroyed, everything stored inside disappears. Of course, unless you've configured some form of external storage or mounted a persistent volume. And this behavior is actually by design, and it's also what makes the container lightweight and consistent. So each container starts from the exact same image, and gets its own isolated writable layer. So no matter how many containers you launch, they all share the same immutable base layer, and after it, each one has its own unique writable space on top of those read-only layers. Of course, this also means that the writable layer isn't meant for long-term storage, and it can also be tricky to extract data from it, since you can't really easily access those files directly from the host system, and you can share them with other containers. So the writable layer is only temporary and isolated per container, and it vanishes when the container stops. It's actually perfect for stateless, repeatable workloads, but not really for storing important data. So containers are really designed to be disposable. Yeah. And now that we've seen what the writable container layer is, let's zoom out for a second to see how do all of these layers actually come together to form the complete file system a container uses. So every container image is built layer by layer, and each layer captures a snapshot of file system changes, like a new file is added, or a file is modified, or a file is removed. And once a layer is created, it becomes immutable, so it can never be altered. And if you need to change something, you don't really edit the existing layer, but you just add a new one on top of the last layer. And when the container starts, all of those layers from the base system up to your app are going to be stuck together. And to make it work seamlessly, a special technology steps in, and it's the union file system. And this union file system is going to merge all those read-only layers into a single unified view. And from the container point of view, it looks like one complete file system. So even though underneath it's actually a combination of many layers working together. So you can see this in the diagram here. So on the left, we have each layer that exists independently. And then on the right, we have everything that merge into one unified file system. And that's what the container actually sees at runtime. So now let's explore what happens the moment a container tries to change something inside that structure. So at runtime, every container starts from the same foundation, and those read-only image layers we talked about earlier, we said that they never change, but containers still need the freedom to modify files or create logs or update temporary data while they're running. So here's how the system solves that. So whenever a process attempts to edit a file from one of those lower read-only layers, the system doesn't touch the original, but it copies the file into the container writable layer, and the modification is going to happen in the writable layer. So the original stays clean, and the writable layer gets its own version. And the container continues as if it had modified the file directly. And that's a copy and write in action. So we copy first, then we write only to our own space. And if you look here at the flow on the screen, the process is really simple. So process inside the container tries to modify a file, and then the system duplicates it from the underlying image layer, and a new private copy is created inside the writable layer. And finally, the edits takes place only in the writable layer. So the lower layer remains untouched, and that's what keeps everything consistent and isolated. And this mechanism is the reason containers can share the same image but behave independently. So every container has its own writable layer. So any runtime changes happen in complete isolation. And it also preserves immutability. So the base image never changes, which means you can run hundreds of containers from the same image, and every one of them starts from the exact same clean state. Now that we've seen how containers isolate changes and preserve immutability through the copy on write, let's look at why this layered architecture actually matters in real world DevOps. So it's not just about how containers actually work, it's really about what this design enables. So it enables efficiency, speed, and scalability. So each layer in a container image isn't just a piece of a file system, it's really a reusable building block. And when you create new images or spin up multiple containers, the system doesn't need to rebuild or to re-download everything. So it simply reuse existing layers that are already stored locally or in a registry. And that's where what you're seeing in this diagram. So we have multiple containers. They all share the base image layers, while they keep their own small writable layer for runtime changes. And the result is that we have less disk usage because in-change layers are shared across containers. We have faster image builds since we only need to rebuild the modified layers. Smaller downloads because when you pull an image, Docker only transfer the layers you don't already have. And it's really the ultimate caching mechanism, but at the infrastructure level. And this is, architecture also gives containers their most important traits, which is speed and reproducibility. So every container built from the same image starts from the exact same base, and your app is going to behave the same whether it's running on a developer laptop or on a production cluster in the cloud. And because those lower layers are immutable, you can always trace and verify the exact environment that's running your code. And that's really huge for debugging, compliance, and overall system reliability. So now that we've seen why this layered architecture is so powerful, let's see now what happens to data inside a running container. Because even though containers feel like a mini virtual machine, they really behave very differently when it comes to storage. So every container you run has its own writable layers. That's where all changes in the runtime are stored. But here's the key. That writable layer exists only for as long as the container exists. So once you stop or remove the container, that entire layer, and of course everything inside it, is going to be deleted. So it's really temporary by design. And that's why we call containers ephemeral, because they're meant to be short-lived. They are, of course, lightweight and easily replaceable. And you don't fix a container, you simply rebuild it or redeploy it. So here you can see in this diagram on the left we have a container without a volume. So the writable layer disappears when the container stops. And on the right we attach an external volume, and that's where persistent data lives. So the base image and all its layers remain untouched, while the writable layer acts more like a scratch space. So this separation between ephemeral container storage and the persistent volumes is one of the smartest design choices in containerization. So containers stay stateless, so that makes them easy to scale, easy to restart or to replace, and the images remain clean and consistent since no runtime data are going to pollute them. And data that truly matters, so like database or logs or user uploads, can live safely outside the container, so in a volume or a mounted directory. And it's really the best of both worlds. So we have temporary compute and persistent data at the same time. So what you need to take away from this video is that everything we've talked about, from image layers to the writable container layer, all comes together to create one of the smallest storage models in modern computing. So a container isn't just a running app, it's really a carefully stocked structure that's built from immutable image layers that never change, and we add to it a temporary writable layer added at runtime, and all these layers are merged through a union file system, which makes the container see them as a single unified environment, and that's what allows it to run just like a normal system. But of course, it's going to be lighter, faster, and fully isolated. And now, when something changed at runtime, the copy and write mechanism kicks in. So instead of modifying the base image, it makes a private copy inside the writable layer, and that ensures the underlying image stays clean, consistent, and reusable. And here's where things really get powerful, because these base layers can be shared across multiple containers. Builds and deployments become incredibly efficient, and you don't have to rebuild or to re-download everything, because only the layers that changed are going to be rebuilt or redeployed. And that's the reason why the pipelines now can ship software in seconds or instead of minutes. And you really need to remember that containers are ephemeral, but your data doesn't have to be also ephemeral. So all persistent information should live outside the container in volumes or in external storage. So you can freely destroy or recreate containers without losing anything important. And that's it for today's episode. So now you know how container layers actually work. And in the next episode, we're going to see what is a container registries. And if you enjoyed this video, don't forget to like, share, and subscribe to keep learning with me. See you. Bye.